like the product of the sines formula. There's a product of sines, product sine cosine, product cosine cosine. For your homework, there's a place where you have sine times cosine. In order to do that, you need to be able to rewrite it as like a sum of sines, right? So ew. Disgusting. Anybody remember the product identity for sine so I don't have to derive it? Anybody? All right, fine, I'll work it out. So we have sine of A, we'll say sine of theta times sine of beta, 1 over 2i, e to the I theta minus e to the minus I theta, 1 over 2i, e to the I beta minus e to the minus I beta, which of course is minus 1 over 4, e to the I theta plus beta, plus e to the minus I times theta plus beta, minus minus e to the I theta minus beta plus e to the minus I times theta minus beta, I think. Could be wrong about that one. No, these should both be minus, which is good because that gives us 1/2 of 1/2 e to the I theta minus beta plus e to the minus I theta minus beta minus 1/2 e to the I theta plus beta minus e to the minus I theta plus beta, which is to say 1/2 of cosine of theta minus beta minus the cosine of theta plus beta. So this is the sum n equals 1 to infinity b sub n, the integral from 0 to L of what? Of apparently cosine. I'll bring the half out if you don't mind. B sub n over 2 cosine. Now here I'm thinking theta equals to n pi x over L and beta equal to p pi x over L. No relation to the previous beta in this lecture. Well, some relation, but not the one that you might want, I don't think. Anyway, so as you notice, theta plus beta is what? How about theta plus or minus beta? Ooh. So we've got like a pi x over L, and you either got, n plus or minus p, yeah? So we get n plus a p, my bad, n minus a p, pi x over L minus the cosine of n plus a p pi x over L, all dx. What do those give you? We get like sine, right, of n minus p pi x over L divided by, times an L up here, and then there's an n minus p down here, and then minus L times the sine of n plus p pi x over L divided by n plus p. This thing gets evaluated from 0 to L. What happens? We get sine of pi times n plus p, or sine of n minus p times pi. That's an integer multiple of pi. Sine of an integer multiple of pi is 0. Both of these are 0, right? Looks like everything's 0. I guess Fourier's didn't work, did it? But what's the issue? There's one place where this calculation is bogus. Right? What's that? At L. No, L is fine. Like if I plug in x equal to L, the L will be canceling. L will be canceling with the x. You know. Oh yeah, but that should happen. We want that. That's the ice bath condition. Good though. Yeah. How about this? In my formula, I have divided by n minus p, have I not? This would make sense when n is not equal to p, right? But when p equals to n, we need a different integral, right? So this calculation is only legit in as much as p is not equal to n. So this is all for, I should really just say for n not equal to p, you know? And then we have plus the integral from 0 to L of when n is equal to p, so b sub p. And then what's that? That's sine squared of, let's say, p pi x over L dx, right? And so what we got, I'm going to do it here if you guys don't mind, is we have b sub p times the integral from 0 to L of, what 1/2, right? 1 minus the cosine of 2 p pi, or 2 pi p x over L dx, yeah? But that cosine does integrate to 0 because we're looking at a cycle of, an even number of cycles of cosine. If you like, this integrates to sine. It integrates to sine when you evaluate that sine at 0 and L at 0. So the only thing that actually contributes non-trivially is this 1/2, which ends up giving us b sub p times L over 2. So therefore, b sub p is equal to 2 over L, the integral from 0 to L of f of x times the sine of p pi x over L dx. And that, my friends, is the formula for the Fourier coefficient. To calculate the coefficient for the Fourier series, we multiply the given function we're interested in expanding by either a sine or a cosine, depends on the context, but in this case a sine, and we just integrate over the interval that's interesting. So if we actually had an initial temperature distribution, we could do these integrals and find the coefficients and then put the answer together. I'm not going to do that today. I'll do it like next time we have a lecture, but next time we'll have a lecture actually will be a review session for test 2, right? Is this on test 2? No, this is not test 2. This is for quiz 5. So this is not on, this. Everything I've said today is not on test 2. This is all for the last story arc of the course. We just got ahead a little bit. So, yeah? Did I call it mission 5? Oh yeah, mission 5, I'm sorry, but take home quiz 5. My apologies for the grading on mission 4. It's kind of not great, like not at all graded. So, sorry about that. But the grader was not making any, mission 3 I meant, I'm an idiot. Don't worry, mission 4 will be graded severely, carefully. All of your mistakes will be found. All right? What's that? I'm collecting mission 4 on Tuesday, yes. Let me show you guys something. So I'll probably, I'm thinking when we come back after the test, I may spend a day just on whatchamacallit here, Fourier series. There's actually a, believe it or not, sometimes I cover Fourier series in calculus 2 if I have a really good class, because it's like a natural extension of power series, you know. But come on, computer. I just wanted to show you guys a picture of one or two before we end. And if you guys got questions about the homework, feel free to chime in. We got a couple minutes, literally a couple minutes. But so this is a handout. It's actually an appendix to Stewart. Stewart has an electronic appendix on Fourier series. It's intended for like a Calculus 2 audience. I'll try to post a link to it in the announcements. But if you look in here, he actually calculates it for like this one, the square wave function. So f of x, 0. Well, this is a periodic square wave, so it's like 0 here and then 1 here. And he calculates the Fourier series. He actually builds that explicitly by calculating the integrals that I was just talking about. So it's some pesky integration, fine. But after you get through it, you get these. So like the first approximation, the second approximation, the third, 7th, 11th, 15th. As you see, as you go further and further, you get closer and closer by adding more and more signs to like representing something like a square wave or whatever. All right. So anyway, I just wanted to show you that. You guys have any questions about the homework? I can load it up. If you don't, that's cool. We can just call it a day.
Can you do 77?
77? I can try. Mission 4. I'm sorry. I was just talking about mission 3. I got mission 3 on the brain. 77. Oh yeah, this one's ugly. I mean, like I said in the announcement, like the integral, solving the differential equations in part A and B, these are formidable. Like I'm not sure I'm going to be able to do them when I actually have time to try. Looking at it, I started with one of you. We worked it out to like a cubic after making a v equals y over x substitution, but it's still quite nasty. And I don't know about the other one. I know part C is quite doable. That's not bad. So if you can't actually do the integration in part A and B, like don't sweat it. Just try, and if you can, you can. If you can't, it's okay. We'll give you most of the credit for trying. Yeah. If you at least write down the differential equations that you should try to solve, that'll be enough for those, okay? What I was trying to do is to illustrate the 3 different cases for two differential equations and 2 unknowns, right? Like we either have a repeated root where we need the generalized eigensolution, or we have distinct solutions, we have 2 exponential solutions, or we have the complex solution. Those are the 3 cases for a 2x2 system, and I wanted to see what this problem looked like in each of those cases. It just so happened that for 2 of those cases are like horrible. Yeah.
Should something this complicated be on our test?
I think part C would be totally reasonable for the test, yeah. And I think problem 76 would be totally reasonable for the test, right? Problem 76 would be totally reasonable. Anyway. Sorry about those. Thanks, guys.